It suggests that even if Penrose's physics of objective reduction is correct, the brain is simply the wrong kind of environment to make use of it. Proponents of the standard computational models argue that this is precisely why they are more credible. They rely only on robust, classical, electrochemical processes that are known to operate effectively in the brain's messy environment. They don't need to invoke exotic, fragile quantum states that seem to violate our understanding of thermodynamics and cellular biology. For these critics, the decoherence problem is not just a minor hurdle for Orch-OR, it is honestly a fatal flaw. Therefore, any defense of the quantum mind has to provide a compelling answer to this challenge. It's not enough to have a beautiful theory about gravity and consciousness. You also have to explain how the biological hardware could possibly protect its quantum operations from the relentless onslaught of decoherence. The theory needs a shield. It must propose a plausible biological mechanism by which microtubules can isolate their quantum computations from the warm, wet chaos surrounding them, preserving their coherence for timescales that are orders of magnitude longer than physicists would normally expect. The entire viability of the Orch-OR model really hinges on this crucial biological detail. The proponents of Orch-OR have not ignored the decoherence challenge. Stuart Hameroff and his collaborators have actually put forward several counter-arguments and proposed mechanisms that could, at least in theory, fend off the thermal noise of the cell. Their primary defense centers on the specific structure and environment of the microtubule itself. They argue that the initial damning calculations made by critics like Tegmark were based on oversimplified models that just didn't capture the true biological complexity of the system. The microtubule, they contend, isn't just a passive structure floating in the cellular soup. It's a highly organized and potentially shielded environment, uniquely suited for protecting quantum states. One key proposal is that the tubulin proteins within the microtubule lattice do not act independently, but in a collective, synchronized manner. The superpositions might be distributed across many tubulins in a way that makes them more robust to local disturbances, a concept known as collective excitation. Furthermore, they suggest that the interior of the microtubule cylinder might be filled with a special, ordered form of water. This ordered water, they claim, could act as an insulating sheath, creating an electrically isolated channel down the core of the microtubule, shielding the quantum states within the tubulin proteins from the noisy electrical fluctuations in the surrounding cytoplasm. Another part of the shielding hypothesis involves the very speed of the proposed quantum computations. Hameroff suggests that the processing within the tubulins could occur at extremely high frequencies in the gigahertz to terahertz range. This would mean that many computational steps could take place before decoherence has a chance to set in. The idea is that the quantum state is processed and built up so rapidly that it basically outruns the environmental noise. They also point to the discovery of quantum effects in other warm, wet biological systems, such as photosynthesis, where quantum coherence plays a demonstrable role in energy transfer, proving that nature has found ways to protect quantum processes from decoherence. These counter-arguments transform the debate from a simple yes or no into a far more nuanced discussion about the precise biophysics of the microtubule. Are microtubules truly capable of this level of shielding? Is water inside them ordered in a special way? Can tubulins act in a coherent, collective manner?